exponents.
Thank you. So, French movie director François Truffaut once said that when you start making a new movie, you want to make the ideal movie, and quite rapidly you just want to be able to finish. Okay, so today the goal is to present the proof of the theorem, and then to discuss the test of theorem in the main case, okay, and then to discuss why did we want to prove this with Sylvain, CROVISIER, and Omri SARIG, and then further a generalization of this result that we actually got in the end. Okay, so let's start. Yeah, so the first part is to explain the proof. So you recall the statement, I will give an outline, and then I will be more specific. So this is what I call the main case of joint result. So you take a C-infinity smooth surface dieomorphism, you take a sequence of ergodic measures that converge to an ergodic measure in the weak start topology, and you look at, okay, you suppose that the Lyapunov exponent converge, and okay, by upper semi-continuity, they will converge to some multiple of the Lyapunov exponent of the limit, this beta. So upper semi-continuity tells you that beta is less than 1. Okay, here you make the assumption. So this can be understood as a definition of beta. The two assumptions really are that the limit is ergodic and that the limit has a positive top Lyapunov exponent. Okay, then the conclusion is that you have a bound on the entropy. If you didn't have continuity of the Lyapunov exponent along this sequence, then you lost, you get a non-trivial. This means that beta was strictly less than 1, and thus you get a non-trivial upper bound on the entropy of the measures in UK. Okay, that's what we have been discussing. So what will be the elements of the proof? Okay, we will put together essentially a lot of things, well, more or less everything that we have been doing for some time. So the first will be a fibered version of Katoch's entropy formula that will allow us to bound the entropy of these measures in UK in terms not of a cover of a set of positive measures, but just the trace of this set of positive measures along a suitable local unstable manifold. Okay, I will give a statement later. Then we will, instead of using, since we want to be dealing with information that comes from the derivative, I mean the Lyapunov exponent, we want to be looking at curves. So we will use parametrizations, and okay, we will do it for several reasons in the spirit of Yomdin. We will be looking at pieces of curve which have small size with respect to their derivatives up to some order. Okay, that's the kind of general setting. Then to get something from this way of bounding entropy, we will consider these orbits starting from this set, and we will use the division between neutral blocks and what remain. We worked on the tangent dynamics to see that this beta defined by the gap in the Lyapunov exponent with the limit will give us or 1 minus beta will be the proportion occupied by long natural blocks. Okay, and then there will be 1 minus beta okay, beta is equal to 0, that this means that the neutral block will have everything, but actually in this case, the theorem can be just deduced from Riemann inequality. So if beta is between 0 and 1, then there are neutral blocks that cover this proportion 1 minus beta, and the remaining proportion beta is not covered. So we have to redo something, and here we will just use, okay, so then once we have a division for each orbit, we have a division of its time interval between 0 and some large integer n. So we do what we did to prove the dilemma, and what people often do, of course, is to, so we have some combinatorial diversity, which is where are these blocks? Okay, we call the position of the blocks types, and for convenience, we just want to fix this data. And fortunately, when the neutral blocks we consider are very long, then there are few possible types. So we can just focus on one, essentially, and forget the rest. Okay, and once you are looking at orbits that start from this mysterious set with a given type, so you know where the neutral blocks are, then you just apply. So first, the key lemma for the neutral blocks. We saw that if the beginning of the neutral block is ni and the end is ni plus 1, we have a bound, which is some Lipschitz constant divided by the differentiability up to technicalities. For the remaining, the complementary interval, well, here we don't have to do much. We just use topological entropy. So topological entropy, the first cost, well, you have the definition of topological entropy, but here we don't know if these complementary blocks are long or not. So there is a constant, okay, which may become bigger and bigger the smaller the scale you're looking at, and the closer you want to be near the exact topological entropy. Okay, this eta is just the error. Okay, and then this is if we were just covering by dynamical balls, but we are working with parametrizations. So there is a multiplication by the usual Yomdin cost. Sorry, here I missed the main term, which is this lambda of f hat divided by r minus 1. Okay, which comes in addition to the number of dynamical balls. Okay, so we have this, we will have this, this is what we are, the game we are going to play. At the end, we have these two types of intervals. On each, we have a bound, and we want to, at the end, to get a bound whose exponent is arbitrarily close to this thing. And here you can imagine that what happens is that here, taking R very large, this is essentially nothing. Okay, small exponent. And for the other guy, you have the topology, the exponent is essentially the topological entropy, but this other guy, they fill a fraction beta. So this is why we will get the bound. Okay, that's roughly, I mean, that's the global idea. Is any question? Okay, so this is the formulation of this, how you can bound the entropy using, looking at an unstable curve and using parametrizations. Okay, so you look at some dieomorphism. We put in dimension 2. Okay, we take an ergodic measure, hyperbolic, so one positive, one negative exponent. Okay, and we have what we call its unstable disintegration. I didn't want to talk precisely about it. I still don't want to. Okay, you fix some numbers, and then what we say is that if you have some subset F of positive measure, if you have x0, you take a base. I think of it as a base point. Okay, with the following property that you can parameterize the the local unstable manifold at x0. Okay, so this with something of CR size epsilon hat. So maybe you need to look at a small piece of the unstable manifold, but the property that we need is just that we need that the curve that we are going to look on the curve that we parameterize, this sigma. Okay, some set of parameters such that its intersection with the set that interests us which will be a set of good points where we have good estimates, like fraction of neutral blocks. We want this to be a positive measure on this fiber. Okay, so if you have this first, and if you are able, and hopefully we will be able to find a family of parameterizations which have this property of admissibility up to time n for each n. Okay, so let me remind you, it means essentially that when you compose each piece, it means that you divide this curve sigma, and on each piece, the composition with any iterate up to n still has a small CR size bounded by epsilon hat. Okay, let's forget about big N. Okay, so here I include, we have chosen some R. Okay, and if we get this, then some family of parameterization like this, then we will have this bound. The entropy of this ergodic measure will be bounded by the growth rate of these parameterizations. That is the number of their elements.
Am I right that we are sigma C are regular, so small pieces are also small CR?
Yes.
So Yomdin is not here.
No, exactly. So here what I should say is that Yomdin is not here.
Yomdin is a neutral.
Yes, this is if you, Yomdin will be here to produce parameterization with the small cardinal. Here I'm just saying if you get parameterization of a piece of curve with essentially positive measure, then then you have a bound on the entropy.
And this small pieces are small CR because we are in the CR.
Yeah, it's a piece of unstable, so it is as smooth as the map. Here it's what is here. So we speak about CR size. Why? Because this is, we want to be able to say what we want.
I just okay. That maybe here we don't need this family of parameterizations, smaller and smaller. This script R, and this is just for any you choose.
Well, it depends. Yeah, it's true. It's true for any family of parameterization.
Nothing special here.
But you have to find one with small cardinality that grows slowly. And it is here that Yomdin and the smoothness will be useful. It's like these parameters, epsilon hat.
Number of these things, same diameter of this little piece which grows to unit size.
Yeah, this is true for R equals to 2. I mean, you need Pearson theory. This is true for R equals to 2. But if we just assume F to be a C2, then we won't be able to get a very good estimate on the number of this. So it's what I tried to say in this first remark, that here we don't have to take, for this statement, I mean, abstract statement, without saying what is the disgrowth rate, we don't care about all these Yomdin type parameters. Okay, it's just that we are going to apply it to a CR curve that will be very smooth, because it will be an unstable manifold, and we are assuming that our manifold is that our dieomorphism is C infinity. This will allow us to know that this is small, but to have this bound abstractly, we don't need anything about it. It has nothing to do with Yomdin. Okay, just you can find a parametrization. Well, you need epsilon hat to be not hugely. No, you don't. You could take them equal to 1, and it would be fine. Okay, there is this trick that I mentioned more or less when I spoke about how you prove that the tail entropy is 0 when you have C infinity. It's the same. That is, once you have a parametrization with bounded size, an admissible parametrization with bounded parameters, you just, if you want to find a delta n cover, you just take a delta dense set in your abstract interval, and you get a cover like this for at any scale. Okay, so this is just so here the parameters are just because we want to apply it to a case where we have a good bound, and when F is just C2, we don't have a good bound for that number, but abstractly it doesn't depend on that. Okay, so once we have a set of positive measures, since we have a disintegration, we will automatically have a set of positive measures of base point with so that the measure of the trace of F is positive. Okay, and if we are worried about the exact size of the unstable local manifold, we shouldn't, because all we care is that we have something of positive measure. So if it is, if the signal norm is big, we don't care. We just take a small piece that meets the set F on with positive measure, and achieve the bound by epsilon hat this way. So there is no problem in applying this. Okay, so that's the game. Now the game is to see that what we know allows us to make this like we want. Okay, and it would be a reparametrization over the T. Sorry. Sorry.
What is F?
So F, it's a set of points where we have the estimates given by the ergodic theorem. Not Pearson, like, for instance, the fraction of long natural blocks. We have seen that for the measures, well, we need some ergodic property of our orbits, and this is F.
Okay.
Okay, so we choose our parameters. I don't want to speak too much about that. Just observe that we have this constant in the topological entropy estimate, and this is one of the main reasons why we have to consider long natural block. Okay?
Is this theorem or just state?
I make it so. So you have to choose. You remember we said that we can find L natural blocks for L arbitrarily big. Yes, what?
Stated the theory. Are you going to prove it?
No.
No, okay.
Be reassured. Okay, it's really this is just an application of bounds that are included as a small kind of lemma in Le Drapier-Young or even in Young paper.
This theorem looks easy, I understand, due to the fact there is no Yomdin.
Yeah, there is no Yomdin. It's really. There is a question of this, but to as it is stated,
You want
to take all.
Separated things.
Yeah.
So you take distance between them or the.
Yeah, there are various ways to prove it.
I want to count with scales. Can I do it in any dimension, or is it important that it's surface?
No, here it's important that the unstable manifold at dimension 1. This is why we are talking about curves. Okay, if the unstable dimension was bigger, we will need to still to cover as the same thing would tell you that you have to cover the trace of a set of positive measure inside an unstable manifold. So if it's dimension 2, you have something of dimension 2. Now you're no longer dealing with curves, including in the Yomdin part where you want to build this reparametrization. So things become much more complicated. Okay, so we have a constant to kill. We kill it. I mean, we know that we will have a combinatorial factor to kill. We kill it also by taking L big and so on. I mean, it's not very interesting. So now this is about the set F. Now first we want to observe that for the unstable lift of any measure so the unstable lift is this nu k hat plus. Okay, so for these points, we have seen that when k is large, however big is big L, we have such an estimate. Okay, the proportion occupied by neutral blocks with lengths bigger than L is almost 1 minus beta, almost everywhere with respect to that unstable lift. So that's this one is a full measure set. So that was from the analysis of the tangent dynamics. The other comes from the key lemma. In the key lemma, there was a set U hat, this set U hat that was built. Okay, that was the set where we had this lemma about essentially the fact that we are on graphs and so on. I don't want. Okay, you certainly remember it. And this is the set U hat, and the key lemma allowed us to build it with measure arbitrarily close to 1. Okay, so we have this, and now when we take, okay, so this was first for mu hat. Okay, for the second one, we stated it in this way. The other in the key lemma, we just spoke about mu hat. Okay, mu hat is the limit of the nu k.
No, you. Neighbor.
Well, U is some set that the key lemma tells us there is, you give me a limiting measure mu hat. I give you and some parameters like gamma. Then the key lemma gives us an open set U hat, such that this is the set where we are essentially on a continuous graph, on the graph of a continuous function. Okay, so it is the set when we are to get the estimate of the key lemma, which is the bound by which is to say that there is no entropy during neutral blocks.
It's related to neutral blocks.
Yes, it's something that we need from neutral. We need to be okay. So we proved that this set is of a big measure for the limiting measure. Okay, so therefore it is, and it has its boundary can be chosen to be of zero measure for that measure. So therefore, when k is large enough, this is also true for nu k almost every point. Okay, and now we do the usual thing. So we fix, so this first step fixes k, okay, or say that k must be, and then we can, here we had a set of measure 1, and this was in the limit. So we can just now find a set of positive measure, it could be a set of measure close to 1, we don't care, and an integer n0, so that we have this inequality for all points in this set f, and for all n larger than this constant. Okay, so that we can, okay, there is just, here it's the lift, the unstable lift. So really f is a subset of the surface. So this is, we want this for x hat, a lift, and the unstable lift of the points. Okay, but nu k hat plus is just the image of nu k by the unstable section. Okay, so that's the choice of f. Now, when we have a point of f, we define its type up to time n just by saying where are the good blocks. So what are good blocks? The good blocks are the maximal natural blocks, okay, of big lengths as usual, okay, but with the extra condition that we need in the key lemma, okay, that the visits to this mysterious set U hat really do occur with frequency close to 1. Okay, this is exactly the condition that we need to apply the key lemma to this. So this set of good blocks is a set of disjoint intervals of lengths bigger than L. So therefore, the number of possibility is small on the exponential scale, as small as we wish, just by taking L big. Okay, that's the usual thing. Now, so since there are few types, we can just pick one and focus on that. Okay, so now we take a point, we focus on the part of the curve contained in this set F and with a given type, so a given position of the good blocks. Okay, so now we do the construction, well, as usual, also inductively. We start with, okay, we take the curve as it is given. And now at each step, which will be at each beginning of an interval cut by this partition, cut in fact by the good blocks, we refine our parametrization by applying the relevant lemma to the curve that we have at this iterate ni. Okay, so we had at ni we have already built by inductive assumption this parametrization Ri. Okay, so we need to find an admissible parametrization up to the next time. That's what we need to do. We only care about this, the set we are looking at. And now we will see that what we want, we will get what we want, which is for a good block, we have the key lemma that gives us a bound like that. And for the complementary intervals, then we have the estimate with essentially the entropy. Okay, each time we have a Yomdin extra cost. Okay, and once we have this admissible reparametrization, essentially for at least for the time difference to the end of the block we are looking at. Okay, we use the concatenation lemma that is really easy and that we know to get from Ri and all the reparametrization for each piece. Then we get the parametrization admissible up to the end of the interval we were discussing. Okay, so now we do we count what we have built. Okay, we started with 1 and we multiplied by one of these two numbers depending whether you're on a good block or not, and you get this bound just by saying that okay, the total length of the good block is about this 1 minus beta times the n. Okay, so to do it seriously, you have to remember that you just fix the type, but okay, it adds an extra error, but you don't care. And then you first let n go to infinity to apply the Fibert-Katok formula that we discussed before. Okay, and then you let the error go to 0. So to make the error disappear, you have to let r go to infinity and eta goes to 0. When eta goes to 0, it requires that you are looking at the set U hat in particular becomes more and more complicated. So you need more and more the measure mu k hat plus to be close to U hat. Okay.
Yes, so the key place where you use Yomdin is this relevant lemma. And
yes.
Which was the relevant Yomdin lemma it was before?
So it's the lemma that, okay, let me, okay. So that's the key lemma. Okay, maybe I just keep this record. Let me see. Yeah.
Here's formulation.
Let me, yeah,
where is the proof?
The proof of the key lemma was last time. So, I mean,
just idea how you use the CR.
Oh, so what you use is that it is this. So, okay, let me see it in this simpler setting where in fact, you see also the need for high smoothness is in fact the same.
This was the example I gave.
So
sine 1 over x.
Yeah, let's see. So you have the entropy. So, okay, sorry, there is no R here. So the definition of the entropy tells you that you have such a bound when you want to cover by dynamical balls your set, the whole projective extension. Then you have essentially exponential h top times n balls, okay, up to something, and you have some constant. That's just the number of balls, dynamical balls. Now we cannot work, since we want to use the tangent, we want to be on a curve. So we want to, so we started with this piece of unstable curve, and now you have to imagine that the unstable curve, okay, now we are looking at some image of the unstable curve. So near some point it is nice, but near other point it is not nice. And now you are looking at the image of a dynamical ball, which is something not so nice.
XR sine 1 over.
Yeah, these are the points that stay close to each other during all the time up to this time n. So they could have been cut. It's not that all around ball. Okay, so now you can have things where like this. Okay, so you could say, okay, but if I am naive and I want just to take, I say, okay, I have started with a curve So I'm still on a curve. Okay, you have this problem that not only you have this one, but it's possible also that you have points that go very far. And now Yomdin, the point of Yomdin tells you, don't worry, if you have counted the number of dynamical balls, if you can restrict yourself to one dynamical ball, then you can find a small number of curves that will, whose image will contain everything that you need. Okay, so Yomdin, even for this kind of trivial estimate where we use just the definition of the topological entropy, just to be able to say that we are continuing to work with curves whose derivative, even just first derivative, doesn't explode, we need Yomdin. Okay, otherwise we don't know here how even the first order, I mean, how is the curve? It can be like this example, xr sinus 1 over x, that can become extremely wiggly when you look at a small scale. So you don't see it, at least for some time, when you look inside everything happens inside balls for a lot of time, but eventually it grows. So this is the Yomdin is a fundamental to.
Did you prove this? Or?
Well, this is easy from Yomdin. I mean, well, this exact statement you won't find it in Yomdin, but you find a statement. Essentially, Yomdin's theorem is this.
You didn't prove of Yomdin.
Well, I tried to, but no, this part of Yomdin is not difficult because it's what. Well, you have to have the ideas. Yeah, in dimension 1, I explained it to some guys here. They can tell you whether they found it. Yeah. So this. Yeah, Yomdin, the key point of Yomdin is that inside dynamical balls, when you are looking at a very smooth dynamics, you can reparametrize, keeping the derivatives bounded, and the number of pieces doesn't explode. That's so that we need it for all the time. So for the complementary intervals, we can just treat them in just one swoop. You just apply the definition of the topological entropy, and then you are inside a dynamical ball of order the length of your interval, and then you just can apply Yomdin. Okay, or in the other dilemma, you have to apply Yomdin every once in a while. But it's you need it already here. Okay, this is what I have been saying. Okay, so it's just that you need to control the curves and not just the points. And it's possible, and Yomdin tells you, yes, it is possible. Okay, so that's actually all. So once we have done this, we have the main case of our theorem. Okay, just because. So as I said, the idea is you produce these natural blocks that come from the fact that you have in the limit mu hat, you see some stable part, so part of is the negative Lyapunov exponent. Okay, the combination gives you this of the positive and the negative exponent give you these natural blocks where there is no expansion. Okay, when you do the computation, you see that the fraction of the time occupied by these natural blocks is given by is the same as the drop in the exponent or the jump, maybe, I don't know. And now you have to actually do the estimates. So you need Yomdin because you have to know that you are always dealing with curves. And even for such simple estimates, you really need Yomdin. And the fundamental reason why you have to work with curves and not with dynamical balls here is that you want to exploit these, what the Lyapunov exponent tell you. And so you have to have a curve that gives you a direction. Okay, and this was the key lemma, which is the part where really you have to understand more what is going on. Okay, essentially you are propagating. You want to see that the curve do not grow when you are in a neutral block. And what I can say, but I don't want to repeat what I said before for too long. Okay, you have the fact that you consider a lift of a curve on the projective bundle. It doesn't grow below because above the derivative, the product of the derivative since the start of the block is less than 1. So it doesn't grow above. In fact, the length of the curve is like the product of these derivatives times the epsilon of the beginning. So usually it will, in a neutral block, it will start by decaying. This length will be decaying exponentially fast, and then it will grow back. Okay, so you, at first, as long as you can use the derivative along the unstable direction, you have this bound on the length below. Okay, and you have to use this U hat. This U hat tells you that, okay, it's nearly as good as if you were exactly on a continuous graph. So therefore, when you control below, it gives you some control above. Okay, so therefore you can really apply the information from the tangent to the curve, and you get the key lemma. And once you have the key lemma and you know Yomdin, then you just put the things together and you get the theorem. Okay, so that's the proof of the main case. So yes?
So still, where this R-1 in the denominator appear?
Okay, because we apply Yomdin to the lift.
So in Yomdin somewhere.
Yeah, so typically in Yomdin theory, you have the log of the Lipschitz constant divided by R.
I understand that this is my example X.
Yeah. So here,
but I just ask where in the proof of this appear?
well, here, for instance, it's very simple. You have your number of dynamical balls of order n, and then you apply Yomdin. And Yomdin, it's exactly the statement of Yomdin.
So you didn't repeat this part of Yomdin.
Well, we repeat it because it's a very simple. I will repeat it for ourselves because it's a very simple part when it's a very simple when you are on curve. And here, the 1 over R.
Calculation involving.
Well, I can tell you exactly where the 1 over R comes is that Yomdin has this fantastic idea that, contrary to everything I believed before, it's actually interesting to do Taylor expansions. So you want to do a Taylor expansion, but you want to control the error. So how much do you have to zoom for the Taylor expansion to be good? Okay. It's exactly this guy. You have to you have to zoom something like this. Okay, you have to go to this scale. Okay, but here we are dealing with the lift, so it's not the Lipschitz constant of f, but of f hat, and f hat it is only a CR minus 1, but it's exact, but it's really a Yomdin result, which in dimension 1, I will put it in the notes eventually, is really simple. I mean, once you have the idea. Okay, so I don't know, maybe that's a good time to make a break. This is what we have been discussing for. Yeah, I anticipated your question. No, of course, it's a good question. just even if you want to work with curves with bounded C1 size, which would be enough for the entropy estimate, you are stuck because you don't know that they don't. How much refinement do you need to make? And this is what Yomdin tells you. Okay, so we make the break.
Okay. 10 minutes.
So welcome back. So eventually, this afternoon I will put at least the version that I have of the old slides here and send them to Felix. Okay, so now for this last lecture, the goal is to tell you what are the applications, first of the main case, why did we want to do that and what did we get? And okay, since I'm constantly saying the main case, it means that there are other cases. Actually, we have a more general result, which has more applications. Okay, so the first I will speak about the main case and its application. The first generalization we will see is instead of asking for the entropy of the measures to converge to the full topological entropy, which forces the measure to converge to a measure with maximal entropy, we will allow any ergodic limit. Okay, and we'll see what we get from that, and it will have application to dimensions of ergodic measure. Yeah, and now and finally we will relax the assumption that the limit is ergodic, since it is quite artificial. Okay, we'll see that the statement becomes more abstract, but still it has important consequences. And then I will talk about, I will make some remarks and recall the papers that you can read about that. Okay, so that was so below we have the main case, above we have the main case. Okay, and now why did we want to have this case? Because actually, because it shows, it has the following corollary, very technical, which tells you that actually if you have measures whose entropy converge to the topological entropy, and if you look at their unstable lift and you look at the accumulation points, then in fact the accumulation points are still unstable lifts of hyperbolic measures, not necessarily ergodic. And this, this is a whole problem. I cannot enter into it, but the idea is that you will be able to consider, you will have some kind of compactness property for measures with large entropy, and from that you will deduce some uniformity properties. Okay, and then this led us to the notion of strong positive recurrence for diffeomorphisms. I say for diffeomorphisms because it was a notion that was introduced by Gurevich and then SARIG for countable state Markov shifts. Okay, so how does it look for diffeomorphism? Okay, there is a notion when you want to study the hyperbolicity, you have the Lyapunov exponent, and maybe the next kind of object, more technical, are the Piecin blocks. What is a Piecin block? It's a non-empty compact set on which you have uniform hyperbolicity estimate. That is, you have a splitting everywhere above this compact set. okay, with a stable and unstable direction. And for instance, the stable direction is contracted uniformly. Okay, so it's unique. This is the K we have. This is the number chi. Okay, we have contraction by chi times the iterate K. Okay, and there is an extra property that is relevant, which is.
So the exponent is minus chi times K plus.
Yeah, if you, so the stable exponent, for instance, will be less than minus chi, less or equal than minus chi. Okay, and symmetrically for the unstable direction. Okay, and you need something more for Cassin theory. I mean, this was introduced for Cassin, by Cassin for this theory, is that when you move along the orbit, this is the integer n, the constant may degrade and may increase, but slowly on the exponential scale. This is the exponential epsilon times the absolute value of n. Okay, when you move forward or backward in time, your constant can grow. Okay, so this tells you that, well, okay, I don't want to say more. This is on this set, Cassin can build a local, stable, and unstable manifold. Okay, so these are sets very relevant to study non-uniform hyperbolicity. Okay, and so what we deduce from this continuity property of the exponents is the following: that if you take a smooth surface dieomorphism with positive topological entropy, then you have this property of uniformity with respect to Cassin blocks. So now I will read it. It tells you there is some chi, which is like an exponent or like a lower bounded exponent, such that for any epsilon, you can find a Cassin block with these parameters, such that for any ergodic measure whose entropy is close enough to the topological entropy, the Cassin block will have, the common Cassin block, I would like to say, will have a uniformly lower bounded measure. So all the measures which are with big entropy have to see the same Cassin block. Okay, this is what we deduce from the continuity property of exponent. And this was our goal, actually. Okay, we wanted to prove this property. Okay, and okay, we realized after some time that we needed the continuity of the exponent, that this was the key difficulty. And more or less it was here okay, then why do we like this property? Because indeed, okay, we have, okay, Omri SARIG built symbolic dynamics for surface diffeomorphisms. Back, I don't know, the paper is from 2013, his paper. And there was the question of how good is this symbolic dynamics? Okay, it is, if you look at the value of the topological entropy, for instance, certainly it is not, it is most of the time not a subshift of finite type. Okay, but, and then, okay, how bad can it become? And there was a class of countable state Markov shift, which is almost as well behaved as subshift of finite type from a lot of point of view, which are those which are called strongly positively recurrent. Okay, so the question was whether the symbolic dynamics of Omri in this good setting where you have not only C2 smoothness but C infinity smoothness, do you have this strong positive recurrence property? Okay, and the answer is yes, thanks to the continuity of the Lyapunov exponent that provide some uniformity somewhere, and from which you can deduce this technical looking property. And so this property for countable state Markov shift is known to imply a lot of good results, as I said, very close to what you have to subshift of finite type. In particular, you have exponential mixing that we heard about. Okay. And so there's one nice statement that we can make is that if you have a C-infinity diffeomorphism of a closed surface, assume it is topologically mixing. So we know by our previous work that there is a unique, topologically mixing with positive topological entropy. We know then that there is a unique measure maximizing the entropy. And we also know that it is strongly mixing in the sense of ergodic theory. Then the strong positive recurrence of the symbolic dynamics implies that thanks to work of SIR and SARIG, the exponential mixing, which is the same as we saw in Polyplot's course, that is, you have, so here you can take any Holder exponent, then you have a rate kappa, okay, such that for any two, this plus is on alpha, for any two C alpha, so any two Holder continuous function with exponent alpha, the correlation function decays at the rate kappa. Okay, so this is, and actually, so that's, we have this, okay, and the remark I want to add is that the C-infinity surface setting is what we need to prove the strong recurrence property. Let's call it SPR, the SPR property. Once you have the SPR property, okay, you will have that you can have for any C2 dieomorphism on any closed manifold, any dimension. If you happen to know that you have the SPR property, then you will have this kind of quantity, you will have this consequence and other in the same spirit. Okay, so that was the big motivation.
Please refer to the condition uniform hyperbolicity. What's the point?
Okay, uniform hyperbolicity would be to say that the whole, so Anosov is to say that the whole manifold is a Pearson block with epsilon smaller than pi. Okay, so here what Pearson tells you using Osenedet's theorem, the first step in Pearson theory is to say that if you have a measure without hyperbolic, without a zero exponent, then it gives a positive measure or even measure close to one, in fact, to some sets like this, where you have uniform estimates, but not invariance. Okay, so that's the, okay, and to get into more technical things, the SPR property for the symbolic dynamics means that for any measure with larger, there is a finite subset of symbols such that all ergodic measures, maybe all measures with large entropy close to the maxi, to the supremum, see this finite set of symbols. Okay, they cannot live, they have to have some uniform part that lives on a compact subset of, or let's say on a finite number of symbols.
Uniformity, the fact that it works for all these measures at the same time.
Yeah, otherwise it's just regularity. Well, in Omri's coding, you have a locally compact shift. So yeah, it's all any measure, any probability measure. Okay, you can find a finite set of symbols such that it sees it gives a big measure to the corresponding cylinders. Okay, so here it's really the fact that it's uniform for the measures of big entropy.
So it's a definition of Pearson block, you don't have any measure.
Yeah, you don't have it. He uses it. So in some sense, you can split Pearson theory in two parts. One part, which is to say, if you have a hyperbolic measure, it gives a positive and even large measure to some Pearson block. Second part, if you have a Pearson block, you can build a stable and unstable manifold, essentially like in the uniform theory. Okay, so that's... Okay, so now let's go beyond the ergodic, the full entropy case. Now you can assume you can just assume that they converge to some measure, which we still assume to be ergodic, mu. Okay, and then what we get is more generally that if the if the entropy converges and are positive, then the Lyapunov exponent also converges. Okay, so this idea of kind of continuity of the entropy implies a kind of continuity of the exponent. I say kind because, okay, we never have, well, it's almost never the case that you're really continuous with respect to the weak topology. It's in this sense. And you look at a sequence and you add the convergence of the entropies. Okay, and more precisely, we can formulate with quantitatively with beta. Okay, and saying that what we get is that if we have a factor of beta, which will be less or equal to 1 by a Poissonian continuity, okay, then we have this same type of bound for the entropies. And the proof is in fact essentially the same that we saw, except that during the complementary interval where we used the topological entropy, you use the Kaplan formula for the entropy of mu. Okay, it will tell you that when nu case weak star very close to nu, then it will see the same dynamical balls most of the time, and from that you can get that during the complementary intervals that we saw, and the one which are between neutral blocks, you are in fact bounded not only by the topological entropy, but by the entropy of the measure, the limiting measure. Okay, this is what any question about that? Okay, and actually you can prove that there are examples that show that this statement is sharp in some sense. I mean, the following sense, that there are C-infinity surface dieomorphisms for which you can give me any two alpha, let's say alpha less than beta between 0 and 1, and someone can find you a sequence of ergodic measure that converge to an ergodic measure with positive entropy, such that the limit, so that you have this formula here, and that here the limit of the entropies is equal to alpha times the entropy of the limit. So any alpha beta, like there exists. Okay, that for all. Maybe there is a measure, an ergodic measure, and for all alpha beta. And beta is 0. there exists a sequence of ergodic measure like in the theorem, which convert weakly to mu, but so that the exponent, the top exponent converge to beta, and the exponent of the limit, and the entropy. And it has to do with homoclinic tangencies and kind of perturbative techniques that Christian told us about. So I don't know in this construction, I don't know how to make it so that mu is a measure of maximal entropy. So I could not say that the sharpness for the main case of the theorem, but if you take an ergodic measure with positive entropy, you cannot say more than the fact that, okay, the loss for the entropy is bigger proportionally than the loss for the exponent. Okay, so a corollary of this is upper semi-continuity of the Hausdorff dimension of measures. So you have two restrictions which are limiting, I mean, they are really limitations. So one is that we have to bound away the entropy from zero. Okay, if the entropy decays to zero, we can say nothing. And it is only about ergodic measures. Okay, so usually you like to know that you are upper semi-continuous because you want to say I have a compact set, so I will achieve the supremum. Here, of course, the other set of ergodic measure is not a compact set. So it is true. I'm not completely sure what you can do with it. Okay, and the proof is using the previous formula to know that you lose more proportionally on the entropy than for the exponent. It tells you that these ratios, entropy divided by the top exponent or entropy divided by minus the bottom exponent, that these ratios are themselves semi-continuous. Okay, so you deduce from the statement of the theorem that these ratios are semi-continuous, and then you apply the formula of Less and Young for a dimension of ergodic measures on surfaces, probably with positive entropy. Okay, so here you really use the fact that it's really, and maybe something I should say is that we have, one can think, I don't know how interesting it is to make this remark, but you have the red inequality that tells you that the entropy is less than the top exponent, I mean, for the ergodic case. And here we have some kind of, I don't know how to call it, but it's the loss. Thank you. It's the loss of entropy, which is less. Okay, it's not the loss. It's this ratio, which is kind of the inverse of the loss. Sorry, this is okay. Okay, so here, once you have this, you have the semi-continuity of this ratio. Any question? Okay, so now that's the general statement. You can imagine why I didn't want to start with this one. Okay, so now you take So we are always talking about surface, a smooth dieomorphism of closed surface. We take a sequence of ergodic measures, but now we don't want to assume anything about the accumulation point, except what we can get just by passing to subsequences. So we can get that there is a weak limit. So sorry, we can get that there is that the unstable lifts have a weak limit, which is a little bit stronger, but it's just passing to a subsequence than saying that the measures below have a weak limit. And we also assume that the top Lyapunov exponent and entropies converge. Okay, so that's free. What is not free is the assumption that these limits are positive. Okay, it's a restriction to what we can say, that the same that we had in the ergodic case. Then there is a decomposition of mu hat, which is this limit of the unstable lifts, between two parts, mu 0 hat and mu 1 hat. Actually, so now I can tell you well, quickly about mu 0 hat is in fact the measure restricted to neutral blocks. Okay, so you have to do it properly, but that's the idea. And now what we say is that there is such a decomposition, such that then the limit of the top Lyapunov exponent is beta times the top Lyapunov exponent, but not of the limiting measure, but just of the part where you have excluded the neutral blocks. Okay, you see, I have renormalized in this statement mu 0 and mu 1 are renormalized, they are probability measure. So really this part is beta times mu 1, right? And this is what I see beta times mu 1. Okay, and they are just the projections. And the limit of the entropies, as before, is bounded by beta times the entropy, not of the whole mu, but of mu 1. Mu 1 may have bigger or lower entropy than the projection of mu hat. That's okay, and you can characterize, or at least in some cases, you have these properties anyway. So that, okay, if beta equals 0, then mu 1 hat is not really defined. Okay, since it appears with a 0 coefficient, you could put any invariant measure that you like, but otherwise, mu 1 hat gives you the top Lyapunov exponent of its projection just by integrating the dilation. Okay, I'm not. In fact, mu 1 hat has a stronger property that if you put almost every point for the projected measure is hyperbolic. I mean, has positive and actually also positive, let's say, to that positive top exponent. So it's, and mu 0 hat, I'm not saying that it has almost everywhere 0 exponent, that would be false in general, but the average dilation is 0. Okay, so from these properties, you can recover the ergodic case. Okay, because you will see that this mu 0 and mu 1 will be made from the stable and unstable lift. Okay, but as we saw when we were proving the theorem, the coefficient that will appear will not be beta. In fact, here you can compute the coefficient from there, from this property. You have the stable and unstable lift, whose average dilation is are the two exponents, and they have to you have to take so the stable lift, which correspond to negative average, but then a part of the unstable lift to compensate and go back to zero. Okay, so and this, if you do that, you in the ergodic case, you can easily, this tells you what is mu 0 hat and mu 1 hat, and you recover the same. Okay, and it's really, okay, this is what I said about mu 0 hat. It's defined by looking at long natural blocks. In some sense, you have your measure, you take a typical point. It has, by definition, the definition of typical is that it's empirical measure is the measure you are talking about. But now you remove what is not in the natural block, what is the long natural blocks. You take proper limits with respect to some parameters, and this is how you get this guy. Okay, and then you do a more sophisticated version of the proof. What I can say, okay, is that you have to be careful. Well, the estimate for the complementary intervals, okay, the entropy bound becomes more complicated because you cannot use directly Katok formula. Katok formula only works for ergodic measures. If you try to apply it to a non-ergodic measure, instead of seeing the average of the entropy of the ergodic component, you will see the essential supremum. Okay, so what you have to do is to cut your measure mu1. You look at its ergodic decomposition. You subdivide it into pieces where the entropy of the ergodic component is almost constant. Okay, so you can imagine that you have only finitely many ergodic components. And then you have this measure nu k hat plus that converge to that. What does it mean? Well, you can think about our proof about the natural blocks. What did we do? We said, okay, we are converging to some mix between the stable and unstable lift. Therefore, what happens is that you have very long intervals because of the invariance, in fact, of these ergodic components. You have very long intervals where typical points are copying the behavior of one, let's say, of the stable component, and then very long interval where they are copying the behavior of the other component. So now this idea, you can just apply it to a finite sum of measures. You will get that the typical points for nu k hat plus copy the behavior. So for a very long time, they copy the behavior of the ergodic component that have some entropy. So you get, for this time, you get a bound with this entropy. And then for some other time, but very long interval, they copy the other guys. So you see their entropy and so on. And in the end, what you get is the average of this entropy of the entropies of the ergodic component. That is exactly the entropy of the measure, with the usual entropy of the ergodic measure. But you have this extra complication that comes into play. Okay, so now we have a question about the statement. Okay, so now we have this statement. So we can say things about arbitrary limits of ergodic measures. Well, we don't have to say what can we do with it. So there are applications of the existence of physical measure, and more precisely SRB measure. So let me recall for us in dimension 2, SRB measure, so SRB for Sinai-Ruelle-Bowen, we heard it from Mark, are the ergodic measure, so that the entropy is equal to the top exponent and this is not zero. Okay, so what we can prove using the previous statement is the equivalence between these two properties. So the existence of such a nice measure, provided it has entropy lower bounded by some constant, h, and the fact that, okay, we have, you see this equality is exactly the equality case of Ruelle inequality. Okay, so this means that to satisfy this equality is to maximize something. Okay, in other words, to maximize the difference. So here, what we are, okay, so you can, it's like, so it's really a kind of, well, not a kind, it's an equilibrium measure, but with respect to some nasty potential. Okay, so what we say is that we don't know if such a measure exists or not in general. Well, it can exist and it can also fail to exist. But one condition for one characterization of existence in positive entropy, or at least, is the fact that you don't need to know that you have a measure, you will have a measure, sorry, that achieve this equality, so achieve zero pressure, to call the things by their name, exactly when the supremum is zero. So you only need to know, well, if you happen to know that the pressure, which will be defined like that, if you forget about the condition. So here you can call it the pressure for measures that satisfy this lower bound on the entropy. If it is zero, then it is zero exactly when there exists a measure that realizes the equality among these measures with lower bounded entropy. So that's kind of characterization of the existence of an SRB measure of positive entropy, well, an SRB measure by thermodynamical formalism. Yeah, another way to describe SRB measure is that they are absolutely continuous along the unstable foliation. And in fact, it's known, I'm not sure who proved it, if it was Le Sang-Yang. It's here that it's equivalent to the fact, I mean, this absolute continuity along the unstable manifold, to the fact that the dimension is 1. Okay, and the dimension by Le Sang-Yang formula or some relative of it is given by this ratio between the entropy and the Lyapunov exponent. And so what we say is the same type of thing. If you can approximate unstable dimension 1 among measures with entropy bounded away from 0, then it's equivalent to existence of an SRB measure with the same lower bound. Okay, that's so for this, it's just use. So essentially, you would like to use the first or the second statement with an ergodic limit, but here you, well, when you are told that this is 0, okay, it gives you a sequence of measures ergodic with entropy is bounded away from 0. So by Ruelle, the Lyapunov exponents also are bounded away from 0. Okay, you can assume that it converges, but you do not know whether the limit is ergodic or not in this abstract setting. So what you do is you use the general version.
And 5%.
Oh, sorry, it's new. Every time it's new. Thank you. Okay, so what you do is you use the general version of the theorem. It will tell you that almost all ergodic components of the limit have to satisfy for instance, that this is 0. Okay, and then you observe that because of this, also maybe because of this bound, it cannot, some ergodic component may be the trivial case where entropy and topological and some top exponent are 0, but they cannot be all like that because on the average, the entropy is positive. Okay, and this is similar thing. Okay, so that's well, that's nice, but I don't know exactly when these conditions are satisfied or not. Okay, something it turned out we realized, especially by discussing with David Burguet, that our techniques, the same techniques that we use, can be used to prove Viana's conjecture in the case of infinity smooth on closed surfaces. Okay, what is it? The condition is that you have a positive Lyapunov exponent almost everywhere, actually in this weak sense that you look at the Lynch loop of you look at the superior growth rate of the norm of the differential. Okay, you assume it is positive on a set with positive Lebesgue measure. Okay, and then we can prove that there exists an SRB measure. Okay, what does the proof look like? Well, I will just say that, okay, this assumption gives you a set of positive Lebesgue measure where you have expansion. Doing some Fubini argument, you can see that there is a curve where you see a positive length of points such that you extend tangent to the curve with a positive exponent. Okay, and then we use these points which have good growth to define, sorry, so now I need to, so you have this set, and you have this positive measure set where, okay, some lambda, well, it's not exactly this lambda, but I don't know. Okay, and now you select among this subset. So this is, you start with something here with, let's say, T of your curve, and now you, with positive measure. And now what you do is that you consider a sequence of subset which will decrease, but not too fast. So they are exponentially small, but with a small exponent. Okay, and then you consider points inside these good subsets. Okay, these points, they will define by iterating them. So let me measures which are nearly invariant. Okay, I'm skipping a lot of things. Okay, just to say that, okay, you have this, okay, that's just some argument, and then you have a congruent convergence to some mu. Okay, you can lift things, you put hats everywhere, and now you have a convergence, and you can apply a version, you can prove a version of our theorem below, above, previous theorem, sorry. So which means that you have this 1 minus beta times some natural part. Okay, and here what you will have is that you will have that lambda plus you will get an inequality like that. It's by comparing. So, okay, what you will, where does it come from? It comes from the fact, okay, now you want to reparametrize the curve restricted to this decay. Okay, and you want to know that, and you get a family of parametrizations. And on one side, you know that they have to, well, the number of elements here cannot be smaller than what predicts these positive exponents, because the length is expanding at that speed. So certainly, since you are covering this set, well, you have to, and since the derivatives are bounded, the number of pieces has to grow at least like the exponent. And on the other direction, you can prove that the entropy of mu1, similarly to what we have in the general case, is bounded by beta times the exponent of mu1. What this is like in the theorem. I mean, the objects are slightly different. So, okay, and once you have this, but you compare this with real theorem, you see that you must have the equality that characterizes SRB measure. Okay, so to finish, on this, I just want to say, so David Burger has different techniques, which actually gives him a stronger result. But the point here, I mean, is that it's really the same approach as our study of Lyapunov exponents and their continuity.
What do you mean?
Well, so what we show is that if this set has positive measure, there is some SRB measure. What he shows is that the basin of this SRB measure cover the set here, which is a natural thing. But for this, he needs a more geometrical study of what happens. Okay, so I feel it works more. But he also, well, there are obvious always similarities also. So, yeah. So I mean, the proof have some elements in common. But yeah, what I would say is that really we just apply our ideas from the previous theorem to these curves, and we get some information about exponent and entropy. So we get existence of SRB in this way. He has a more geometric approach, so he gets more information. Okay, it works also. Okay, I don't know. So let's say some remarks quickly. So from the more or less simple to the hypothetical. So the paper is written because actually it doesn't cost really. Instead of looking at sequence of measure for a single diffeomorphism, you can just assume that mu k is fk invariant, provided that the diffeomorphism converge in the C-infinity topology. Okay, we have a result about finite smoothness, but with error terms like these Yomdin things, and they are ugly. So everybody, all the time when you do Yomdin, you have lambda over R, and we have this lambda over R minus 1, and it prevents some applications. So it's actually David Burger has another approach where he doesn't have this type of problem. Okay, so one thing that you may have noticed is that even in the ergodic case, so you have, okay, we proved the bound. Now you can say very well, you have this beta. Now let's look at what happens for the inverse. Okay, and one of the exercises in the very beginning was that the sum of the top and bottom exponent is a continuous function. because it's just the integral of log of the Jacobian. Okay, therefore, the discontinuities of the top and of the bottom Lyapunov exponent, they are just a simple, they are proportional to each other. I could not say by which constant, but they are proportional. So you can see what happens if you do the things, at least in the ergodic case, for the inverse, and you get a different bound, which is somewhat disappointing since, okay, we had this thing, we say, oh, it's the same fraction that appears, we have the right statement, we are very pleased with ourselves. Well, unfortunately, it's, well, the invariance is not correct. Physicists would be disappointed. Okay, this I already said. Okay, and what I do now, I just want to say that everything that we do is strongly one-dimensional. Okay, and that you can ask a very interesting question about higher dimensions. And maybe some cases would resemble what we have done, but it's for us, so it's completely open. Okay, so thanks a lot for your attention.
Can your results be extended to close on three-dimensional manifolds?
Sorry?
Can your results be extended to close on three-dimensional manifolds?
I don't know. I would hope so, but I haven't thought about it. So that's the key thing is whether you can compute the entropy by looking at curve or something, or pretending to do like that. So it's a good question.
So in case if you consider sequence of dieomorphisms,
Yes.
convergent to some limit, does the result on bound for Hausdorff dimension extent? I mean, will you have something that is greater equal than lim sup of HD of UK?
I think so. It's what we do is really we apply Lesson-Young formula. So
That's like the speaker.
Workshop and
we have this afternoon.
And then we still afternoon session at the university program cooperating with the program.
Also, but it's a different program.